Dear students, we are by the time familiar with the Boltzmann's distribution, otherwise known as canonical distribution, which gives the probability PR that a system at any given instant is found to be having an energy ER when it is in thermal contact with a heat bath or a reservoir sharing a common temperature T. And from the expression for PR, the probability, we have seen the canonical partition function, which we represented as Z, which mathematically was acting like a normalization factor for the probability. And we have seen that the canonical partition function has got a lot of physical significance because it acts like the bridge between the statistics of canonical ensemble and the thermodynamic of the system that we are trying to analyze. And in the very beginning of our discussion, we have made it clear that there are alternative ways for deriving the canonical distribution function, and we can have two approaches. One of the approach we have seen, we considered the equilibrium between a system and its reservoir, and we studied the statistics of the equilibrium or the energy exchange that is happening between the system and the reservoir. And in the second approach, which we are going to discuss in this video, we will be discussing the statistics or the way in which a certain energy E is shared amongst the members of the ensemble. So this method is the actual ensemble formalism, which will be following finally the method of most probable distribution. So we will see both the methods, whether you do the first approach or you follow the second approach, which we are going to discuss right now. The end product will be the same expression PR that we are by the time familiar with. Okay, so now let's embark upon the alternative derivation for the canonical or the Boltzmann distribution of energy. So what we are going to do here, we are considering an ensemble of systems. So let's say we are having an ensemble of let's say n number of systems. Okay, so I'm using early letter En. So here we can see each of this system is having energy which is E1, E2, E3, E4, etc. So you know, in canonical ensemble, the macro state of each system is described by the parameters N, V and T. Means that all of them share the common macroscopic parameter N, V and T, which remains fixed for each system, right? And since the temperature is kept to be constant, means the system is supposed to be in equilibrium with the surrounding reservoir, we can say that we permit the energy of all the systems to vary. So theoretically speaking, the energy of the system can vary between 0 to say a maximum value E. Okay, so the energy of the system can be, some of the systems energy can be 0, some systems can have energy E1, some are having E2, E3, etc. up to say, if there are R different states, R different micro states, okay, then we can say that there will be R different values of energy it can be, right? So now let's consider the total number of systems in the ensemble. Remember, you know what is an ensemble? Ensemble is actually a collection of the original system with its replicas or with its virtual copies. Okay, each of which will be having the same macro state NVT here, and will be in different micro states that the system can access, right? So let's all together say that in our system, in our ensemble that we are going to consider today, let there be total number of n systems. Means n elements are there in the ensemble. And let me say that these n number of systems, see that I'm using curly letter n to denote the number of systems in the ensemble. Don't get confused with the number of particles in a system. Remember, number of particles in a system we are denoting by ordinary capital letter n. So you can see that here n that I'm using in the diagram. This n and this n are different. Try to distinguish between the two n's that I'm using. Here the curly letter n denotes the number of elements in the ensemble. Okay, so which will be actually a measure of the different types of microstates, different number of microstates that the system may possibly have, right? So the n be the number of systems in the ensemble sharing a total energy. Let me say that the total energy that is shared by all these ensembles together, all these systems together, it will be clearly letter E. So both the things. Remember, I'm using ordinary capital letter E, E1, E2, E3, etc. as the energy possessed by each element or each system in the ensemble. Right? So the diagram here is showing as schematically the ensemble here. So see, let there be like system number one. System number one is characterized by number of particles n, volume v, and of course all of them are having same temperature T. All of them are in thermal equilibrium. So let this be the rth system. So this is system R. System R. System R means actually it's a virtual copy or mental copy of the actual system, which may be considered one of these things, right? So this is a system R. So you can see here N, V, T are common for all the members of the ensemble. Okay, and you can see for the first member, system number 1 in the ensemble, the energy is taken to be E1. System number 2 in the ensemble, energy is taken to be E2. System number 3 is having E3. Likewise, we can say that there are large number of sufficiently large number of. We cannot exactly say that how many members should be there. It should be having members large enough such that it is able to represent each of the accessible microstate suitably, proportionate to the probability with which it can occur. I cannot say that the number of systems in a canonical ensemble is equal to the total number of accessible microstates. Actually, the number of systems in the canonical ensemble will be very large, and it will be more than actually the total number of accessible microstates, because we can see that we have seen that the density function rho is proportional to, or rho is equal to some rho 0 into e raised to minus what? Beta h. So beta e. So this is the way in which it is there. Means that the density function of different microstates in a canonical ensemble is not a constant. Actually, it is depending on the energy of those states exponentially, right? So there is an exponential dependence. Means we cannot say that all energy states are having same number of members in the ensemble. So due to that reason, one thing to be very clear, so depending on the density function, there will be large number of systems in the ensemble, and it's one thing is for sure that any accessible microstate will be represented by at least one system in the ensemble. At least one system in the ensemble will be corresponding to every microstate, and certain microstates will be having greater number of representation in the ensemble because its probability maybe is greater. Lesser the energy, greater will be the probability that that system is being occupied at a given temperature. We have seen from the previous discussion, of Boltzmann distribution. We have seen that lower at any given temperature, the probability that the lower energy state is occupied will be always significant compared to the probability of occupancy of a state with larger energy. Means in canonical ensemble, we cannot say that all microstates are having equal probability of being occupied. But remember, remember one statement that the probability of equal a priori. That statement is actually applicable for what? Microcanonical ensemble systems. Why? In microcanonical ensemble systems, we have seen that all the systems and its virtual copies are having same energy. Since they are all sharing the same energy, the probability of finding a system in any of those energies was equal. Right? unlike a system in the microcanonical ensemble where the probability of finding any state was equal a priori, the probability of finding a system to be in a particular microstate will not be the same as the probability of finding the same system in another microstate as far as a system under my canonical ensemble is concerned. Because in canonical ensemble, energy is a variable, and the probability density rho or density function rho is not a constant. Okay, the density, if the density function is a constant, we can say that all the members will be having same probability of occurrence. Okay, so it is enough that each of the state is represented by a single member in the entire ensemble. But unlike that one, canonical ensemble, different microstates will be appearing with the different representations, different numbers in the ensemble. Okay, those states which are having greater probability will be having greater representation in the ensemble, and those which are having a lesser, lesser probability will be having their number also proportionately small. So it's all decided by the density function rho equal to rho 0 e raised to minus beta e. Okay, so energy decides, energy of the system decides their respective count given ensemble. So out of that idea, this is the thing. So I'm taking some time to tell you the fact. Doesn't matter, our derivation will not be taking much time, but to understand the symbols that we are using and the concepts behind those symbols, certainly we will have to spend some time. Okay, so we are considering once again, back to our description, considering an ensemble of n system. Which ensemble? Of course, it's understood. We are dealing with the canonical ensemble, so it's understood actually. Consider an ensemble of n number of systems sharing a total energy E. Okay, so what will be the total energy E shared by the ensemble? We can say that it will be like the sum of energy of the first system, second system, third system, E1 plus E2 plus E3. Likewise, you can say that. Okay, so let me say that the rth system, let that rth system be having number of particle n, the volume is of course V, the temperature is T. Let me say that the energy of the rth system be what? ER. Right? Now let the symbols, we are bringing in some symbols. Let NR be the number of systems in the ensemble with energy ER at any time T. This should not be giving you any confusion. NR be the number of systems in the ensemble with energy ER. What does it mean? See, for example, suppose there are only one system in the entire ensemble having energy E1. So let me say that there is n1 equal to 1. For example, this is only example. N1 is equal to 1. Now, suppose that E2 is a lower energy compared to E1. And you know from our idea that the states with the lower energy, the chance of their occupancy will be greater. Suppose that N2 is equal to, say, I'm just taking some toy model. So N2 is equal to some 3. What does it mean? There are three elements having energy E2, having energy E2 in the ensemble, right? So how come this N2 equal to 3? It can be sometimes due to the degeneracy. Okay, so you know that if you consider the degeneracy of levels, see, there can be more than one state having the same energy. So it can be due to degeneracy, or it can be due to which one? The probability of its occurrence, which is due to the lower value of its energy at a given temperature. So due to all these reasons, there can be different number of elements of the ensemble in the same ensemble. So that is what I mean. So likewise, see, N3, let there be N3 number of systems. N3 can be equal to 1, then only one representation. N3 number of systems with the energy E3 and so on. And finally, let me say that let there be NR number of systems with energy ER, which represents what? Which represents the system number R. So that is the thing. NR is the number of systems in the ensemble with energy ER at any given time T. Whenever we go for ensemble of systems, we can the condition of the system at a given instant of time T. We arrest the time Okay, and we imagine a collection of all microstates which we call as what? Ensemble. That's why we usually say that at a given time t. Okay, it's not a time average. We are going to take what is known as an ensemble average. So ensemble average is taken at a fixed time. Okay, right. So therefore that is the symbol. N1 out of n total number of systems. N is the total number of systems in the ensemble. They are supposed to be in state 1. They are supposed to be in state 1 with energy E1, right? N2 out of this n systems are supposed to be in state 2 having energy E2. Okay, all these are different microstates. Okay, n3 systems in the ensemble out of total n systems are in state 3 with E3 and so on likewise. Okay, we can say that. Okay, so many E4, E5, etc. Let's say that NR systems out of total n systems in the ensemble are in a state R, rth state with energy what? ER. Instead of nth state, we are calling it as what? Rth state, right? So this is our assumption. And let me call that this is one type of distribution, right? It's not a way of distributing. See, it's not a way of distribution of the elements of the ensemble within the ensemble. Okay, so or we can say that it's a way of distributing the energy, okay, total energy E amongst the members of the ensemble. Okay, so this is, I'm repeating, this is a way of distributing total energy E amongst n members in the ensemble, right? So I can call that, we call this one, this expression, this distribution as equation number 1. So we can say that this is one of the modes of distributing the total energy, E among n members of the ensemble. Now here what is important is that what is the value of n1, n2, n3, n4, etc. These values are relevant, right? So this is one way in which the total energy can be shared between the members of the ensemble. So I can say that the set of numbers, so this distribution is characterized by the set of numbers. Which is the set of numbers that is relevant? The set of numbers n1, n2, n3, etc. up to nr. So means all these coefficients. Okay. So let me represent this set of numbers as set nr. Set nr, where you can say r is equal to 1, 2, 3, 4, etc. Set, I'm calling this set of numbers as, and you know that any given energy can be shared in different ways amongst the systems in any collection. Means there are different ways in which this n1, n3, etc. nr can be made up of. Okay, so n1 can be 1, n1 can be 2, n1 can be 3. Accordingly, what should happen? The n2, n3, etc. the remaining number should be getting adjusted, so that the total number should be equal to what? Capital N. That's the only thing. Okay, the total number of systems in ensemble should be equal to capital N. That is the only constraint that the systems, the ensemble is having. So we can say that these numbers, the set of numbers, what is represented by nr, they the set of numbers must satisfy the constraint, is not? Okay, must satisfy the conditions, We are bringing constraints. I'm writing one condition. It's very easy to understand. What is that condition? First I'm writing sum over r nr is equal to what? Tell me. Sum over r nr is equal to 1. What is nr? nr is out of n systems in the total ensemble, nr is having energy er. So what do we sum over r nr? Means what is the sum of n1, n3 plus etc. up to nr. So the total number of systems in the ensemble, or terminology. So certainly this one should be equal to that sum of total number of systems in the ensemble. So let me say this is equal to A. One more thing, it's equal to capital N. To be sharing N1 system is by number of systems having okay, that is energy E2, that there are some contribution that into E3. Over R, E equal to the total enzyme. The constraint, right? But two, of course, I can say the two, I can say is the total number of what? Two.
The energy fluctuation in a canonical ensemble will be actually very low. So that we will be seeing next. So these are the two expressions, two of the constraints. Okay. Now any set NR, let's proceed. Okay. Any set NR, here I have taken any set NR which satisfies the conditions 2A and 2B. It satisfies the conditions 2A and 2B. You know, is a possible mode of distribution of total energy E among n members of the ensemble. Is that it's a possible mode. Any set which satisfies 2A and 2B constraint equations, it's a possible mode of the sharing of a total energy E, script letter E, among n members of the ensemble. such as 1 can be obtained is given by a weight factor such as 1 can be obtained is given by the weight factor. We are going to define statistically, probabilistically a weight factor. Okay, defining a weight factor. The weight factor is usually represented by capital W. The weight factor corresponding to the set NR. So you'll be writing it as W of NR. Okay, the NR is a subscript. Remember, it's not W into NR. So the weight factor corresponding to a given distribution set NR, that is given by, okay, say I'm going to just borrow an equation from combinatorics. Okay, means the permutations and combinations theory. So n factorial, we can always refer to this one. It's equal to W, the weight factor NR is equal to n factorial, capital N factorial. What is this n? N is the total number of members in the ensemble, divided by n1 factorial into n2 factorial x into n3 factorial, etc. up to nr factorial. So let me call this equation as equation number 3. So don't worry from where this one has come. I think, okay, you maybe you remember, see this type of say equations which you have already used while you studied about permutations and combinations of different things. For example, equation 3 represents the number of permutations of n things. So this is nothing but, remember, number of, okay, W is the number of permutations of, we will be repeatedly using such equations, we will be borrowing such equations from combinatorics, permutations, number of permutations of n, total n number of things, out of which n1 are alike, okay, n2 are alike, etc. right, among themselves by reshuffling. For example, suppose that you have got say 10 balls. You have got 10 balls. I'm just giving you this an example so that you can understand equation number 3 from where it has come. You have got 10 balls, out of which I can say that there are say 3 red, 3 blue, and the remaining 4 are say green. Okay, now see how many permutations are there, how many arrangements, okay, meaningful arrangements are there by reshuffling. Okay, by reshuffling all these balls, you can just get it as, we can say that that is given by W. W will be equal to number of permutations. W will be equal to, see here what is the total number of balls? Total number of balls is what? You can say that is equal to 10. So it will be equal to 10 factorial divided by then n1 factorial. See, 3 of them out of 10, 3 of them are red, means they are alike. So it will be 3 factorial. Then next one multiplied by, again, next 3 are blue. So again 3 factorial. Then into, what is that? Next 4 are what? Green. So again 4 factorial. So this is the number of permutations of 10 balls, of which 3 are red, 3 are blue, and 4 are what? Green. So much in the same manner, you can just compare it. Okay, n1, you know that out of our n systems in the ensemble, n1 systems are alike in what respect? n1 systems are having same energy E1. Likewise, okay, we can say that it's just like they are all states representing same degenerate, say states, right? Okay, so like n2 states are having same energy E2. So we can say n1, n2, n3, etc. are the number of states having same energies respectively. So this is the thing. Now W, we usually call W as the weight factor, or you can just remember, so this W stands for the number of ways. Okay, any of this letter
will help you to memorize what is this capital W. Capital W represents the number of ways in which a distribution given by NR can occur, which satisfies what? The constraint equations, is not? But yet we have to go to the constraints now. Now, our idea, we have to find out what is the most probable distribution. You know that there are a number of ways in which this distribution can occur, but in statistics, what we are interested is in finding out the most probable distribution. Okay, so that is what we are we are worried about. Therefore, the most probable distribution. Remember, this is our focus. The most probable distribution. Hope you remember one particular statement or belief that we are working on. What is the belief? In the beginning itself, we had seen that in the thermodynamic limit, the most probable distribution will reduce to the only probable distribution, and that is the beauty of statistical assumptions. Okay, once we are able to find out probabilistically the most probable distribution in a set having large enough number of members, okay, statistics will prove that the most probable distribution will be the only probable distribution in the thermodynamic limit when you have enough and more number of elements or sample data. So that is the thing. That is why we go for the method of most probable distribution. The method of most probable distribution to derive the canonical distribution function. Most probable distribution set. The most probable distribution set. Okay, I'm just underlining this fact. This is our key idea. So let me represent the most probable distribution set as some NR with I'm putting a star, NR star. Okay, NR. It will be the one which makes. Okay, NR star will be the one. What is the speciality of? Do you remember what is the speciality of most probable distribution? Okay, from our fundamentals of statistical microstates and the counting of microstates, hope you are remembering, the most probable distribution set will be characterized by maximum number of microstates. Is not? The most probable distribution set will be the one which is having maximum members or maximum number of microstates. And maximum number of microstates means in our present language, it will be having maximum value for W of NR. Okay, W of NR given by 3 depends upon the distribution set NR. For different distribution set of NR, there will be different values of W of NR given by equation number 3. So, most probable distribution set NR star will correspond to maximization of the value of W of NR. Okay, so that's what I want to stress. The most, hope you remember that, the most probable distribution set. Okay, see, we just have seen which one was having maximum probability in the case of tossing of 2 dice. That the one having greatest number of microstates is having what? Greatest probability. That's much in the same manner. We extend it to sets now. So, the most probable distribution set, which we denote by NR star, will be the one which makes this W of NR a maximum. W is the number of ways. Number of ways means number of ways of distributing something. That is number of possibilities, or we can say number of microstates corresponding to. Okay, so W of NR equal to a maximum. So this is the characteristic of most probable set.